So this is 6.1. We're starting basically the next part of the whole acids and bases thing, and this is when they react together. So in the previous unit, it was what happens when they dissolve in water, things like what's the pH, what's the concentrations, and now this is where we're putting it in practice. The nice thing about this unit is we have to be in the lab, and we've got lots of equipment to set up this stuff. If you look at the notes for example 1, it says, and don't be surprised if you see this sort of thing on like AP exams or whatever, consider the reaction between acetic acid and sodium hydroxide.
Consider it.
Okay.
Considerable.
So here's what AP assumes. It's that you know the formula of the polyatomic ion acetate, so that you know the formula of acetic acid. So you have to ask yourself, do you know the formula of acetic acid?
It's like HC2H3O2.
But not everybody knows that.
It's CH2.
No.
Okay. So here's your acetic acid. The sodium hydroxide is a little bit easier. We should know what that one is. So this is the reactants for now. I've mentioned this before. AP likes to try to confuse you. And if they were going to give you the formula of acetic acid, remember it looks kind of like a base instead of an acid, just because of the way they write it. They call it CH3COOH. And if you just look at this, you might think, of course, there's an OH, it's a base. But it's not, it's actually dividing here. And so you have your 2 carbons, your 3 hydrogens, and your 2 oxygens. But it's just a different way to write it. So don't be surprised if you see it like this. They pull that often enough. So there's going to be 2 products here. Easy enough to predict. This is just a basic double replacement type reaction. Your hydrogen here is going to react with your hydroxide here. And you end up with hydrogen hydroxide, right?
Why'd you bring it back better?
Because sometimes AP does this. It's not really hydrogen hydroxide, though, is it? It's H2O.
Isn't that the same dihydrogen peroxide?
You'd be surprised how many people on the AP exam will write HOH without realizing that they're talking about water.
It's not wrong.
It's not wrong. You can write HOH, but you should know that it's water, just so you know. So water is one product. It's a liquid, and I've not been writing states. I should. And your other one would be sodium acetate. So Na has a 1+ charge. The acetate. So if they wanted you to write this entire reaction, you would have to write states, because yes, it is important, and you can't really tell what it is if you don't write the states. But when it says write the balanced net ionic equation, I'll show you what we can do. And this might answer your question. So we have a reaction of a weak acid. Let me write this in here. A weak acid with a strong base. So this weak acid, only about 1% of it dissolves. So if we're going to write the net equation, on this side, we have to write this, because it's not 100% dissolving, and so a lot of them are, in fact, this acetic acid version here, where they're together. I have to put the aqueous on this. But then when we look at the second reactant, it's a strong base. So everything of this strong base is going to be sodium ions and hydroxide ions. Remember, in the net equation, we don't want to show spectators. So let's take a look here. Sodium is aqueous here. Sodium is aqueous here. That makes it a spectator. That means we're going to leave it out of this. And so for the base, the only thing we have to write is hydroxide.
So no state there, just.
So this is where you don't have to write the state, because if you write the charge, it is implied that it's aqueous. This is according to AP. And so you have to understand that sometimes you have to write the states. This is the only case where you don't have to write the state. Personally, if I was being graded on something, I would probably write aqueous anyway, but you'd be fine like this. If there's a charge, they know it's aqueous. So products. One product is water. So liquid water in a net equation would be liquid water. State has to be there on that one. Because water is going to have the same formula whether it's a solid, liquid, or gas. There's one more piece we have to put in here. So this acetate, it shows up on this side and it's a weak acid, so they don't really come apart that well. Over here, it has to be there. So this acetate right there needs to show up in the equation. And so this is what your net ionic equation should look like. Acetic acid, when combined with hydroxide, gives us water and acetate. As far as the balancing goes, you've got hydrogen and hydroxide making one water, one acetate on either side, so it's already balanced. So this is your net equation right here. It's balanced. Do you have any questions on that one?
What?
Why what?
What do you mean? Like, what's the benefit of taking sodium?
Because sodium is a spectator ion. If we wanted to know everything that was involved, we would just stick with the first equation. But we only want to see the things that are actually involved in the reaction. It's like if you switched out sodium with potassium, everything might happen exactly the same. And so, I don't know, spectators just don't show up. Things that tend to be spectators: sodium, potassium, chlorine. So group 1 and group 17 stuff tend to be spectators. It's not always the case, like with HF, hydrofluoric acid. It's a weak acid. But a lot of times the things in those groups are spectators. All right, so here we are getting into the actual reaction stuff, putting all this together. It tells us 40 milliliters of 0.1 molar acetic acid is combined with 30 milliliters of 0.1 molar sodium hydroxide. So let me write these in here. (40 milliliters, 0.1 molar, 30 milliliters, 0.1 molar. Before you jump right into an ice table, You're going to want to put these in moles. So moles of our acetic acid. Remember, this is something I'm talking to Chem 1 about right now. Number of moles is the volume times the concentration. And volume, right now we've got milliliters, and concentration, molar, is moles per liter, which means you also have to convert to liters. So for the moles of this, I wouldn't say you really have to show your work on this part of the conversion, as long as you can do this right. So 40 milliliters is 0.04 liters. Move the decimal place left 3 places. Okay. Times 0.1 molar, which is moles per liter. The liters cancel. 0.00400 moles. And we can do the same thing with the hydroxide. Move the decimal place left 3 to make it liters. Concentration is 0.1 moles per liter. And we're left with just moles. So all of this is the preparation for the ice chart we're about to make. So I'm going to duplicate this page. Probably crash my computer in the meantime. All right. So I'm going to make my ice table here. We decided we have 0.00400 moles of this. 0.003 moles of the hydroxide. So at the beginning, we're going to assume that there's no acetate involved here. And as far as water goes, we haven't produced any water, but you also have to think that there's just a massive amount of water around this, okay? And so water, we tend to leave it out of equilibrium expressions, and for now, I'm just going to not say anything about water. I'm just going to leave this whole column blank, okay? Thanks to a certain someone from last year, L means leave it out of my ice table.
Mm-hmm.
So here's how it works. For every one of these, we're going to use one of these. So which one runs out first? Hydroxide. So this one, we're going to use up this amount. Hydroxide is going to hit 0. Which means that we're going to use 0.003 moles of the acetic acid, which leaves us with a little bit left. again, we're ignoring the water. We produced some acetate in all of this. So we produce one acetate for every one of those things over there. So it's going up by 0.003 moles. So we were calculating the moles of each substance, assuming the reaction went to completion. So we had 0.001 moles of the acetic acid left, 0.003 moles of the acetate left. For the reaction in part B, which is the limiting reactant, acetic acid or sodium hydroxide? It's the one that goes to zero first. It's the one that runs out first. Hydroxide is our limiting reactant. Highly scientific explanation here in my notes. It says because it was all used up.
But how do you know that all of the 0.004 moles of each CH3O2 can be combined with the OH? Because it's not a strong acid. So how do you know?
Right, it's not a strong acid. So what happens is when you put this strong base in here, the strong base will pull the hydrogen off of it. And so for every hydroxide, it's literally just going to take the hydrogen. It doesn't have to wait on it to dissociate, it just grabs it. And so that's how this reaction is just going to happen. So with 0.003 moles of this, it's just going to grab 0.003 moles off of this. And that's how we end up with that. So we don't have to wait on it to dissociate or anything like that. If you, for some reason, decided to try to use this one as the limiting reactant, you would subtract 0.004 here, which means you would subtract 0.004 here, and you get a negative number here. Can't do that. No good. So if you get a negative number down here, it means the other one was the limiting reactant. Classify the reaction mixture in part B as either an acid, a base, or a buffer solution. Why does your answer in part B not reflect the actual final reaction mixture? This is one of those weird things. Unit 5 is pushing us towards, we're going to talk about buffers next unit. Unit 6 is like we talked about buffers in the last unit. And so we have to go back and talk about what is a buffer solution. Simplest explanation. It is a solution that contains both weak acid and its conjugate base. And if you look at this solution, we have some weak acid left. That's our acetic acid. And we have its conjugate base here. That's acetate. So this is one where we can say, yes, it's a buffer solution based on just that piece of information. The end solution has a weak acid and its conjugate base. There's both. So let's imagine for a second, make this real big. Let's imagine that we did something that we didn't have any of this acetate there. All we had left was acetic acid. What kind of solution is it now? It's an acid solution. Okay. Or let's imagine that there was a bunch of hydroxide, so we used all of this and there was this left over. Now we had a basic solution. So those are the other alternatives, but the way we ended up here, we had both acetic acid and acetate. Simplest definition of a buffer solution. It's also important to note, and this is written in the same area, part D. So you want to write this down. One more sentence. This is not the final reaction mixture. This does happen as part of the reaction, but it's not the final, because what happens is the buffer solution needs to reach equilibrium. So the way it's written right now, it's tilted pretty heavily towards acetate. See that? But the way it should go is that most of this should be acetic acid, because 99% of acetic acid should be this form and the other 1% should be this form. And so we're tilted really heavily towards the products right now. And what's going to happen is, to get back to equilibrium, you're going to have this big shift towards the left. These are things that you'll see over the course of this section. Then there's a note that's already on your paper. Whenever an acid is combined with the base and at least one of them is strong, we consider that the neutralization reaction goes to completion. So here's a strong, we can assume that this completes itself. However, if one of them is weak, like in this situation, there's a second process, it's the equilibrium. It's going to follow after this. So step one, we did find the moles of the initial reaction. Step two, use stoichiometry to describe the reaction mixture when it's at completion. But then step three, use concentrations for the equilibrium step. So in example 2, we're going to start talking about these equilibrium steps. Is everybody good so far? All right. So example 2, we are using the same chemical reaction here. I'm just going to write the net equation. Suppose a 0.1 molar sodium hydroxide solution dissolves completely, so we've got 0.1 molar of hydroxide added to 40 milliliters of a 0.1 molar acetic acid solution. The Ka of the acetic acid, 1.8 times 10 to the minus fifth. So we're going to find the pH of the solution in a bunch of different scenarios. In scenario A, it says no hydroxide has been added yet. So there's no hydroxide for the initial reaction for the stoichiometry step. So we skip straight to the equilibrium step. So here's what's actually happening here. This is becoming hydrogen and acetate. So we know the initial is 0.1. Since this is the equilibrium step, we don't really have to worry about volumes right now. We're just looking at concentrations. Hydrogen 0, acetate 0. None of it has dissolved yet. Acetic acid goes down by X. Hydrogen and acetate go up by X. This should be pretty familiar. At equilibrium, acetic acid is 0.1 minus X. Hydrogen is X. Acetate is X. So your equilibrium expression is Ka equals products over reactants start plugging in numbers. We've got X squared on top. On bottom, 0.10 minus X. Get rid of the minus X. Here's your value for X, which means the hydrogen concentration is that number in terms of molar. Let's pause for a second. On the mock exam that you took like a week ago, there was a question like this, and I don't know who it was. Somebody did all of their work correctly, but then didn't put molar. And I had to mark it wrong. There will be more on units later because some units you can get away with not putting and some you have to put. And I'll describe the exact situation of when it's okay to leave off the units. But in that particular question, leaving it off lost a point, and it was kind of sad. So the pH of this is somewhere approximately equal to 3. What we get? 2.87. Okay. So this is the pH of the acetic acid before anything happens in the reaction. Then in part B, we're going to add 10 milliliters of the sodium hydroxide. Here's the hydroxide. Are your ice tables filled in, or are you drawing them by hand? Good. So we've added 10 milliliters of 0.1 molar hydroxide to our 40 milliliters of 0.1 molar acetic acid. So for these to work in our ice table, we need to change it to moles. So change your volume to liters and then multiply that by the concentration. And it gives you 0.00 400, and that's moles. If you're careful, we can make this a little bit easier. Can anybody here be careful? Is anybody in here capable of being careful? No? This is a 1. Here's what you can do. So if you look at this, this is 4 times 10 to the minus third, and this is 1 times 10 to the minus third. And so if you understand that everything in this table is times 10 to the minus third, so here, 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 and here, you can make this a little bit easier on yourself and call it this. But you have to be careful. You have to remember at the very end that you did this, or your pH is going to be 1,000 times, your concentration is going to be 1,000 times wrong. And so it's going to be off by, a factor of 10 to the third. That's 3 points on the pH scale. Okay. So these are used up in a 1-to-1 ratio. So the one with the fewer amount of moles is going to run out first. So we're going to use 1 mole of each of these, and we're going to produce 1 mole of our acetate. Again, water. We don't really care. There's a lot of water around. So then for the equilibrium step, well, let's fill this in, sorry. 3.0 times 10 to the minus third moles of acetic acid left. No hydroxide. And we have produced 1 times 10 to the minus third moles of the acetate. Is this an acid solution, a base solution, or a buffer solution? It's a buffer solution. We have a weak acid and its conjugate base. So here's the easiest way to do the equilibrium step in this situation. I won't make you pull out your AP formula sheet right now. You can look at it if you want, but you don't need to. There's a formula. It says pH equals pKa plus the log, and here's a fraction. And this one's going to be C2H3O2 minus over HC2H3O2. On your formula sheet, I think it says A minus over HA, probably, is what it says. So this means anion over the acid. And so this is an easy way to calculate the pH of a buffer solution. So we know the Ka value. pKa means the negative log of the Ka, which was 1.8 times 10 to the minus fifth. Plus, here we're going to put the log of, make sure you use the actual numbers. Acetate is 1 times 10 to the minus third over acetic acid, 3 times 10 to the minus third. And this will give you your pH of this solution. So it's a lot easier than making a second ice chart as long as you know the basics of plug in the numbers. That's it. So the pKa for acetic acid is 4.74, and whatever all this is. So what do we get for our pH here?
4.27.
4.27. Yeah, something in that range. So it says, what's important here? Because it's a weak acid plus a strong base, do the stoichiometry step first. Since it's a buffer, we use this equation. It is known as the Henderson-Hasselbalch equation. Just know that if it's a buffer, you can plug it in here and find the pH pretty easily. We're going to stop there. We don't have time to do any more. Off the tape.